So, well, let's try to remember what we did last time. Last time we tried to define the product of the smash product of two spectra by basically saying that x raised y to the n we did the following thing. We first chose a subset A of z greater than or equal 0. Then for elements of this subset, we for each element of this subset, which is some beta of n and gamma of n, and take the wedge. The smash product in the usual sense. Very well. And then we basically, if we want to define the value of x smash n for something not in A, we choose the greatest element of A, which is less than or equal our element of z, and suspend the result we have with this greatest element of A less than or equal sufficiently many times. Does everyone remember this construction? And I also mentioned there are other constructions which avoid this this particular arbitrary element, which consists in choosing A and then some beta and gamma, and there are other constructions which we will not discuss in this seminar, and we proved We proved that the homotypic category of spectra is symmetric monoidal if the definition of the smash product does not depend on the choices we make when we construct the product. More precisely, we okay. So, what is a symmetric monoidal category? Does anyone remember? So we start with a category, which is just a category, but we assume that there is a monoidal structure which is basically a functor from C cross C to C, where C cross C is the just the Cartesian product category. So we have a functor from C cross C to C, and on top of this, we need to specify the associativity and commutativity isomorphisms. Well, these are self-explanatory. The associativity isomorphism goes from x tensor y tensor z to x tensor y tensor z. And the commutativity isomorphism goes to goes from x tensor y to y tensor x. And these functors need to satisfy some number of axioms. For example, associativity, the associativity isomorphisms need to satisfy the pentagon axiom, and the vertices of the pentagon correspond to what?
Different way of bracketing a sequence?
Yes, of how many elements? Yes. So this is basically the two ways of bracketing x, y, z. And it's a segment. It's a line segment. And if we think about the possible ways of putting the brackets on x, y, z, w, one gets 5. And these can be arranged in a pentagon so that each edge corresponds to one of these transformations. And there are higher dimensional analogs of this, which are called the isohedra, and we will not need those. For our purposes, pentagon suffice. And actually, let's also specify a unit which is an object of C, and this object has a property that E tensor X and X tensor E are both isomorphic to X. But since we are in the categorical world, we need to specify the isomorphisms, and then there will be some axioms to check which involve all the isomorphisms mentioned in this definition. Very well. By the way, lots of familiar examples of monoidal categories are in fact symmetric monoidal. Well, the one example is sets or topological spaces with the Cartesian product as the monoidal structure. Another example is groups with the direct product as the Cartesian structure, and so on. And or modules over commutative rings. Again, we have the tensor product, which basically inspires the notation I'm using here. So those are all symmetric. Does someone know a meaningful example of a monoidal category which is not symmetric? Well, for groups we have we have the monoidal structure which comes from sets, and it is symmetric. So one example which I think is useful in topology, and I don't know whether or not we'll have the time to talk about it in detail, but it is useful. One can consider a category, basically any category, and the functors from this category to itself. The functors, the end of functors from a given category to itself, they also form a category. And on this category we have the monoidal structure, which is the composition of functors. And this structure is relevant because monoids with respect to this monoidal structure are what people call monads, and these are very useful in trying to model spaces, spectra, and basically more or less any kind of homotopy theory. Okay, well, maybe we'll talk about monads, but let's not get distracted. So, which I already am. Okay, so there are symmetric monoidal categories, and basically, last time we did construct the associativity and commutativity maps, but those maps go from X smash Y for some choice of the ingredients to Y smash X, for example, for another choice of the ingredients, and so on. So the candidates for the associativity and commutativity morphisms, unfortunately, the way we constructed those depend on the choices. So we need to start checking that the axioms held. We need to first specify how to pass from one choice of A and beta and gamma to another choice. Well, so let me briefly explain how to do this. So suppose we have two. Let's start with two spectra. Let's say we define the smash product in two different ways. Let's observe that in either case, the nth component is let me write it like this. S1 which K N L Y M such that the K plus L plus M is N. So the nth component of each product has this form, and what varies is L and M, and well, consequently K as well, because the sum is the sum needs to be N. Now, my claim is this allows one to construct a cofinal so using this, we can construct a subspectrum which is cofinal in both of these. Let's see how. Oh, and let's let's say that both of these are CW spectra. So we want a common cofinal subspectrum. Let's think. How do we construct starting from these well, I can put the question mark. What do we do? Well, we need to remember the condition which I wrote last time, but I didn't write today. So beta and gamma both go to plus infinity, then goes to infinity. Very well. So let me okay, let me put let me choose some component of this form for the first smash product. Then S1, K2 of 1, X L2 of 1. Sorry for several indices, but let me first write this down, and then we'll see what makes sense, what doesn't. So K1, L1, and 1 are the components for the first KL and similarly So we do we have we're in luck. We have chalks of all colors. So let me use yellow to okay. So I take some component of the first smash product. Then I choose a component of the second smash product such that all indices are all indices KLM are greater than those for the first smash product. And so on. I take K1 of 2, smash X L1 of 2, Y M1 of 2. And I again choose the indices in such a way that okay, so here we have a component of the first smash product, and here we have the component of the second smash product. So far, nothing happened. I just made a list of which contains components of the first smash product and the second smash product alternately.
Not clear why for fixed choice.
Okay, so we let's see. So the beta and the gamma functions go to infinity. So we can find these two. Yes, let's think. Okay, so let's also remember that in this definition, both beta and gamma not just go to infinity, they go to infinity monotonically. So every time we increase n, we okay, no, this doesn't help. Every time we increase n, we increase exactly one of the values beta and gamma, but not both. Okay, so you're right. Before we start this procedure, we need to make sure that as n goes to infinity, all three coefficients go to infinity, which is not true for an arbitrary choice of a, beta, gamma. But it doesn't matter. We up to replacing either of these with a cofinal subspectrum, we may indeed assume that all three coefficients go to infinity. Так, значит, то, что все три коэффициента стремятся к бесконечности, значит, этого можно добиться. Давайте сейчас на секундочку предположим. So, assume Ki, Li, Mi go to infinity as for I for I1 and 2, and later on we will show that this is something which is indeed possible. Okay, so so far I have have just a sequence of components of the first product and the second product. And now the question is, how does this help? Well, we if we want this to be a spectrum, we need to define the structure maps. To define those, we need to specify what happens when we increase each of the KLM individually. So actually what we need is a map from the suspension of this thing to the same thing with just one of the indices increased. Well, for K, we just append S1 on the left. But for L and M, let's see what happens when, for example, we increase L. So we start with S1 wedge S1 to the K wedge XL wedge YM, and we need to go to S1 to the K wedge XL plus 1 YM. Well, there's just one map which comes to mind, namely after pushing S1 all the way to just in front of XL, we apply the suspension map of the spectrum X. But there is a problem. we when we swap two factors in a smash product, a sign may appear. And this was actually encoded in the definition of the smash product of the spectra. So we need to put here -1 to some power, and this power is well, basically we swapped S1 with S1 k times, so the power is -1 to the k. Now, what does this mean? Well, this is a map from a suspension. For maps, we know that maps from a suspension always form a group. This group may not be abelian, but it's a group. So if this -1 to the k is -1, we just invert the first coordinate. If it's +1, we do nothing. Now, what happens when we increase m? The same thing, except we need to transpose x to the L and S1. So the result is instead of -1 to the k, we get -1 to the k plus L. And by inspection, after we compose those maps, we get the structure maps of the components we listed as structure maps for the first product, and the second components the structure maps for the second product. Значит, что произошло? Значит, мы выписали некоторый набор пространств. Мы выписали некоторый набор отображений из каждого пространства в следующее пространство. Значит, мы имеем отображение отсюда сюда, отсюда сюда. Значит, что происходит, если посмотреть на эти отображения? Если посмотреть на эти отображения, мы получим в точности значит, структурное отображение первого спектра, структурное отображение второго спектра. Значит, неформально, потому что здесь никаких других отображений быть не может. Значит, если здесь, значит, следите за руками. Значит, если здесь какие-то места подозрительные, то давайте их обсудим.
Имеется в виду, что вот эти пространства, они в новом спектре, который мы собираем, будут стоять на местах К1 плюс L1 плюс
Да. Значит, это будет компонент суммы вот этих, это компонента суммы вот этих и так далее. Значит, значит, вот суммы пробегают не все, но нам достаточно, чтобы они пробегали что такое финальное. А дальше мы все там заполним значит, настройками. Ну, здесь я сказал, что происходит, если мы настроили один раз, но если мы настроили 2 раза, то происходит вот композиция вот этих вот. Если мы настроили 3 раза, то же самое. So, what happened? We get a spectrum. And the even part is cofinal in the second product, and the odd part is cofinal in the first product. And this is it. But we, well, before we explain why we may assume that all 3 components go to infinity, are there any questions regarding this proof? Please note that in the book by Adams, there is another proof which is quite different and more complicated than this one. So so it's not the worst one can imagine. Anyway, now we need to check the assumption. Well, the assumption this one. Okay, we we have this definition. I want to construct something cofinal, which which would have the S1 component going to infinity as well. Let's see what can go wrong. For example, if I take A to be all even numbers, beta and gamma of n both equal n 1/2 n, then I only get S1 to the power 1 max, and I don't get anything else. Either I get no factor or just S1. Well, to fix this, let's rarefy K. No. Let's rarefy A, sorry. The maximum power of S1 is the maximum of okay, to state it clearly, let's let's order A. Let's totally order A. And the maximum power of S1 will be the maximum of AI minus AI minus 1 plus 1. No, minus 1. Basically, the powers of S1 appear when we have two elements of A which have something in between, and we fill it with S1s. Well, very well. So let's let's just replace A by A prime, which is A to the I Okay, so instead of taking all of A, let's take this part. It's very small, but it's still cofinal, and then we actually, if we want this K to increase monotonically, we okay, so 2 to the I is probably a bit optimistic, meaning there could be, okay, Ni. So instead of all A, I take a subset such that the difference A Ni minus A Ni minus 1 tends monotonically to infinity. Well, let's also assume that the sequence Ni itself goes monotonically to infinity. And my claim that this is possible, which is more or less straightforward. So we choose a subsequence. We choose a subsequence of the sequence A0, A1, and so on, such that the difference of any two consecutive terms of the subsequence form a sequence which goes monotonically to infinity. And then we keep only those elements of the product which have indices in this subset, and replace the rest with suspensions. Okay. Are there any remarks, suggestions, criticism? So the what exactly did we prove? For any two choices of the ingredients we use to define the smash product, there is a cofinal subspectrum in both for both definitions of the smash product, which is cofinal in both products. And now we can at least define the associativity and commutativity and the identity morphisms in the homotopy category. And my claim is that all axioms of the symmetric monoidal category are satisfied. And well, as you can probably imagine, at this stage, the proof is a boring verification of the axioms, and I don't think we have time or energy to do this. Okay, before we have a break, we also any questions or comments or criticism and so on. We also need to define the Hom spectrum. So what we just did was the monoidal structure, but we also need the internal Hom. Again, this will only be defined on the level of the homotopy category, not on the level of the spectra themselves. But the definition is pretty straightforward. Same as for the smash product. We start with two spectra, and we want to define the internal Hom, which is usually denoted f of xy. So the words internal Hom mean that f y z mean the following thing. We we should have some f of xy. At least as an element of the homotypic category of spectra, and we this f of xy should depend functorially on y and also on x. So f of x, f of xy is contravariant in x. So this, as opposed to the tensor product, which is a functor from C cross C to C, this is a functor from C op cross C to C. Well, doesn't matter. This should be functorial, and we should have this this adjunction. This f of x. So in other words, f so we have two functors. Sorry. Let's look at this. Let's erase this. This equality is basically saying that something is adjoint to something. What is adjoint to what?
Smash with y and f from y to something.
Okay, so we have smash with y. Is it a left adjoint or a right adjoint? Yes, so this is a left adjoint. Okay, we have the homotypic category of spectra, and we have the left adjoint, which is smashing with y, and the right adjoint. So the left adjoint is here, the right adjoint is here, and the right adjoint is fing from y. Let's see. When we apply the left adjoint to x and to z, it's the same as when we take the right adjoint to y and take Homs from x. Okay, does this make sense? So this is what we want, let's have a break. After the break, we will see two ways of constructing the Hom spectrum.